All right, hello everyone, and welcome to our next video on estimation and problem solving. So by the end of today's video, our goals are to help you learn the following things. First, we'll review dimensional analysis and see how we can use a similar approach to perform estimation. We'll also learn about analytic and creative problem solving strategies. Finally, we'll talk strategies for brainstorming. And we'll explain how to use some real engineering techniques, including structured problem solving and 5 whys. So let's go ahead and do a couple quick practice questions while we get started here. And so first, we have a review question. We have a rectangular box, which is 1.0000 centimeters by 3.00 by 5.000 centimeters. Questions asking, how should we write the volume so that it has the correct number of significant digits? And second question, just something to think about. Which of these problem-solving strategies do you prefer? Take a moment, pause the video if you need, and try these questions. Okay, so let's see how we did. So first question, we know that our volume is length times width times height. And so by that reasoning, we can determine that our volume must be equal to 15.2 for significant, or up to 4 zeros there. But the question is, how many significant digits do we use? Remember, for multiplication, we want to use the same number of significant digits, or sig figs, as the input with the lowest number of significant digits. So in this case, we see that our first input, this one actually has 5 significant digits. Our second input has 3 significant digits. Just remember that these zeros do count because it's a decimal. And our last input has 4 significant digits. So in this case, we need to use 3 significant figures in our final answer. So 15 here becomes 15.0 units here, centimeters here. So therefore, choice B is the correct answer. Second question, there is really no right or wrong answer here. But one thing to think about as we learn about problem-solving strategies in this video is think about what types of problem-solving strategies you prefer. Research generally shows that you tend to be happier and more successful if you put yourself in opportunities where you get to solve problems using your preferred style. So, just something to think about as we continue on. Okay, so let's review just a bit more from our previous video. You'll remember we learned about dimensional analysis. And we learned that dimensional analysis allows us to convert units, or any quantity, allows us to convert quantities by treating the units like algebraic quantities. So remember, our goal is to make the undesired units cancel. So, for example, one way we could use unit conversion is suppose I wanted to eat as many Snickers bars as I could in one day. Let's say I'm eating those mini Snickers bars. So those are 80 calories each. I've eaten a lot of them. So we have these Snickers bars, right? And suppose we want to only eat Snickers bars for a 2,000 calorie diet. So in this case, I want to find out how many Snickers bars can I eat per day to stay within that diet. So if I have 2,000 calories per day diet. So in this case, I want to convert between, in this case, I have 2,000 calories per day, and I want to convert to the number of bars per day. So what I can do is I can say, okay, well, I have 2,000 calories per one day, and I want to get rid of days. I'm sorry, I want to get rid of calories. So I need to make a conversion factor where calories is on the bottom so that the units cancel. In this case, we know that one bar contains 80 calories. So days stays there, but notice the calorie units cancel, and we can determine, in this case, I can eat 2,000 divided by 8 bars, 2,000 divided by 80 bars per day if I were to only eat Snickers bars for a 2,000 calorie diet. So that comes out to something like 25 of those little things. So that's an example of dimensional analysis. And basically the steps we want to do here are identify the units that we have and the units that we want. And then what we do is we give ourselves some space and we try to arrange conversion factors to make the undesired units cancel. So here I wanted to have bars per day, get rid of calories. So I arranged the conversion factors I knew in order to make the undesired units cancel. This approach is very useful not just for converting units, but also for performing estimation, as we will see later today. So why do we bother to talk about estimation? It turns out that being able to estimate stuff quickly is really important to developing that engineering intuition. Remember, we want to be able to have a good sense about whether our calculations are right or wrong. We want to be able to recognize quickly if something is off. And estimation can help us do that. So estimating quickly is good for engineering intuition or spidey sense. In addition, estimation is helpful if you want to do a sanity check to make sure your answer is reasonable. A lot of times we'll be calculating things and working on projects that might not have been done before. And so sometimes you need to reassure yourself that the numbers you're getting are reasonable. So here's the estimation process that I recommend. So first you want to state what you know. There will be something that you know about the problem that you can use to help guide your estimate. Next, you want to list your assumptions. You assume about your problem in order to make it simpler. Usually we have to make assumptions. And we do this because we need to simplify the problem to something we can solve. So we have to make assumptions in order to simplify the problem. And make it easier to solve. Remember, the goal here is to make an estimate. So sometimes if you have limited time, you have to use the information you have available, and you can't worry too much about being 100% accurate. You're just trying to find out whether your answer or your idea is in the right ballpark. So we state what we know, we list our assumptions, then we perform our estimate. And then notice this last point. I think this last one is especially important. We have to make sure that we communicate our final result clearly. So when you share that estimated value, you want to be clear about the assumptions you made. And you also want to report your estimate with the correct significant digits. Chances are, if you are making a rough estimate about something, you're not going to have 10 digits of precision. You might have 1 or 2 or 3. You're not going to have 10. So you want to make sure you report your answer with the correct amount of precision so that it's clear that you're just dealing with an estimate. So you don't want to make people think you are actually able to estimate something to 10 digits of precision. That's usually not the case, and you don't want to mislead people with your final answer. All right, then. So let's look at an example. Sometimes during engineering interviews, people want to see how you think, and so they'll ask you to do some calculations in front of them. And this is one calculation that you might be asked. So in this question, we're being asked how many ping pong balls will fit inside a Boeing 747 aircraft. So, not necessarily something we would actually attempt to do in real life, but the goal of this question is to see how you approach problems and if you're able to make reasonable assumptions and come to a reasonable answer. So let's give this question a try. So let's go ahead and walk through the recommended procedure that I shared, and let's go through it together step by step. Remember, the first part of our estimation procedure is that you want to state what you know or what you're able to easily look up. Let's think about what we know about this problem. Well, we know that ping pong balls are spheres. We also know that if you were to pack a bunch of spheres into a tight space, the spheres are not going to occupy the entire space. There's going to be some void space, right? There's going to be some empty space between the ping pong balls. So we need to decide how we want to handle that space in our calculation. Next thing, we know that most of the people and cargo in a 747 airplane are stored in the cylindrical body. A lot of the fuel and other components are stored in the wings. So therefore, we can get away, if we wanted to, with assuming a cylindrical volume. Also, from geometry class, you may remember some equations for volumes. We know, for example, volume of a sphere is 4/3 pi r cubed, where r is the radius of that sphere. And of course, pi is approximately 3.14. We know the volume of a cube is length cubed, and the volume of a cylinder, we have a cylinder, we know the volume will be given by pi r squared times the height, where the height is the length of that cylinder. So that's what we know. You may know some additional things as well, but you just want to get some ideas out there and think about how you could tackle this problem. Next thing to do is to state your assumptions. So naturally, we're not going to be able to go over to a 747 airplane and take measurements. So we need to make some assumptions to help us solve this problem. So I'm going to assume the following. First, I'm going to treat ping pong balls as 1.5-inch cubes. I'm going to assume that these are 1.5-inch cubes. And the reason for this is because it helps capture the void space in our estimate. Remember, ping pong balls are not going to all fit when they're tightly packed. There's going to be some empty space. So if I treat the ping pong balls as cubes, I can make an approximation for that empty space. Next, I'm going to go ahead and assume that the available storage space in the airplane is a cylinder. So I'm not going to worry about the wings or the other parts of the plane. I'm just focusing on the cylinder as the available space for those ping pong balls. Next, we need to think about how big that cylinder is. And so in this case, I'm just taking some very rough estimates here. I'm assuming that since maybe 10 or 12 people can fit in each row of the airplane, let's assume the diameter of that cylinder is 20 feet and that the whole cylinder is 250 feet long. Also, here's another assumption. I'm going to assume that all of the available space inside that airplane body is available for ping pong balls. So I'm not going to consider oxygen masks, seats, or other stuff inside the plane. I'm literally thinking about how many ping pong balls can I fit inside the entire cylindrical volume. This is why it's very important to be clear about your assumptions, because of course, in real life, we know that we would not necessarily be able to clear out the entire empty shell of an airplane. So this estimate will probably be a little bit higher than what the actual number of ping pong balls could be. And that's okay. We're just trying to estimate here. All right, so now it's time to perform our calculations. So here's our strategy. First, we can calculate how much volume is available in that 747. And remember, we're treating it as a cylinder. So first we find how much volume is available in the total space. Then we can divide by the volume of a ping pong ball. Once we know the volume of the space, volume of a ping pong ball, we can determine how many ping pong balls could fit. So if we go ahead and use volume of a cube, we know if we have a 1.5-inch cube, our volume will become 3.375 inches cubed, or approximately 3.38 cubic inches. Next, we can use the volume of the cylinder. Remember, we assumed a 20-foot diameter, so that gives us a 10-foot radius. We have a 250-foot length of the cylinder. And so if we plug into our volume equation, we get pi times 10 squared times 250, and that gives us a volume of around 78,539 cubic feet. Careful here, because notice my units are different. So we got to be careful when we're dividing those two quantities. All right, so what we need to do next is let's go ahead and convert our cubic inches into cubic feet, because if I want to find my volume, I need these units to match. So I'm going to convert my ping pong ball volume to cubic feet, and then I will be able to solve. So in this case, I go ahead and use a conversion factor, and you can see what I'm doing here is I'm making my units cancel. And notice, one ping pong ball actually doesn't need all that many cubic feet. So I go ahead and take this cubic feet per ping pong ball, and I can divide my overall 78,539 cubic feet from my whole airplane divided by the volume of a single ping pong ball. And I determine that over 40 million ping pong balls could fit inside that 747 jet. That's a lot of ping pong balls. But if you think about it, the cylinder is pretty big as well. Okay, so question for everybody. We just calculated that 40,152,472 ping pong balls would fit in that Boeing 747. So what final answer do you tell your boss? Take a moment and think about it. Well, what do you think? Remember what we said earlier about significant digits? Do we have 8 significant digits in this estimate? Not really, right? If we look back at our calculation, we assumed 1.5 cubic inches. That's just 2 significant figures. Or here, we're looking at 1 significant figure for our radius and 2 significant figures for our length of the cylinder. So our least precise value here has 1 significant figure. So if we go purely based on significant figures rules in our estimate, we can see that the final answer should only be reported using the same number of significant figures as the lowest, or as the input with the lowest number of significant digits. So in this case, that lowest number is one significant fig, one sig fig. So how do we write 40 million with one significant digit? The answer would be choice B. We would tell our final boss, or we would tell the interview committee that based on this very rough estimate, we would estimate as many as 40 million ping pong balls could fit in that 747. Probably would be a good idea to clearly explain the assumptions you made as well. As you might expect, depending on the assumptions you make, the estimate could vary significantly. So once again, just to summarize, our estimate really included only 1 to 2 significant digits at best, so the best answer would be about 40 million ping pong balls. That's one significant figure. And so about 40 million ping pong balls would fit. That's assuming that all the space can be occupied by ping pong balls, and each ping pong ball occupies roughly 1.5-inch cube. I'd also mention what we assumed about the cylindrical body of the aircraft. All right, so one question before we move on to problem solving here. Do you think this estimate is higher or lower than the actual value? Well, think about our assumptions. We assumed that that entire jet would fill completely with ping pong balls and nothing else would be inside the jet. But in real life, we probably have to have other stuff in there, stuff to support the running of the plane, seats, oxygen masks, other equipment. So most likely, this estimate is on the high side. This estimate is probably higher than the actual number. But in some cases, you want to intentionally overestimate or underestimate depending on your situation. Maybe you want to know the maximum possible. Maybe you want to know the minimum possible with wiggle room. So, depending on the situation, you could choose what type of assumptions that you wanted to make. All right, so let's go ahead and move on now to problem solving. And if you've done any problem solving before in other courses or on your own, you might have learned some of these many strategies. Problem solving has so many possible tools and approaches available. And we don't have time to cover all of these tools, but I would encourage you to think about if you have certain favorite tools that you find useful when solving problems. Keep those tools handy and maybe try learning some new ones. So, this is just a list of 26 possible tools you could use to help solve problems. We'll learn about a few more strategies during today's class as well. Overall, when we talk problem solving, we can break problems into two main categories. The first category is analytic problem solving. So, analytic problems are kind of like the homework problems you would do in chemistry class or math class. These are problems that are very clear cut, meaning they're very well defined, and there's usually only one right answer. Right? These ones, you just have to plug in the math and apply logic, science, all of that in order to solve the problem. These problems are very important though. Even if there's only one right answer, you definitely still want to find it. Good example of this is, will this design fail? Do you want to calculate how much load a bridge could support? Or whether a building would survive a big earthquake? These are examples of analytic problems. And our textbook, Engineering Your Future, gives a recommended process on how to solve analytic problems. We'll go through that a little later. The next problem solving category is creative problem solving. In creative problem solving, we use creative thinking to solve slightly different problems. Creative problems are problems which are complex and open-ended, and there's many possible solutions. In fact, there might be many possible solutions, and there may not be one perfect solution. When solving these creative problem solving problems, often we generate new ideas and we have to use a lot of creative thinking. So again, creative problems, they are open-ended, they're complex, often with many solutions. Sometimes we focus on generating something new. And notice this last point. The engineering design process as a whole is considered to be a creative problem solving process. So let's try a quick practice question here. Pause the video if you'd like to try it. So, question here is asking, which of the following problems would be best solved using analytic problem solving approaches? What do you think? So, remember, in an analytic problem, they're very well defined problems, and there's generally only one solution. So, notice choice B, C, and D. Those are all important problems, but there's many possible solutions for B, C, and D. For your chemistry homework, that's usually pretty clear cut. So chemistry homework problems would be best solved using analytic problem solving. So our textbook recommends following 6 main steps when you are doing analytic problem solving. First, you define the problem and make a problem statement. You want to make sure you know exactly what the problem is that you're trying to solve. Read the instructions carefully and review your data and known information carefully. Next, diagram and describe. You want to understand the problem. Next, apply theory and equations and simplify the assumptions. Again, the goal is to turn that problem into something that we can actually solve. Then we solve the problem and notice the last step. We also want to make sure that we verify accuracy to the required level. Let's go through these step by step. So, first question, have you seen this comic before? This is a fun little cartoon, and it kind of illustrates the importance of having a problem statement. Notice that each department, marketing, sales, engineering, manufacturer, field service, notice the customer wanted a little tire swing, but everybody else was solving a different problem. So that brings us to step one. We want to make sure we clearly define the problem we're trying to solve. And be specific. Make sure you're solving the right problem and prioritizing the right things in your solution. Here's an example problem statement. This is an activity that we often do in our labs. So, in this problem statement, we want to determine which solar cell purchasing strategy will give the greatest cost savings over 40 years. It's pretty specific. We're looking for the greatest total cost savings over a 40-year period. Next, we need to diagram and describe. So here our goal is to really make sure we understand what's going on. Here's an example. If we were working on that solar cell cost estimate, we could prepare a table summarizing all the data we know. Maybe these are our different options for solar cell purchasing. And notice that we have various assumptions and data associated with each option. And in this case, we want to decide which option gives the greatest cost savings. Over 40 years. All right, so the next step, it's time to apply theory and equations. And here is where you might also use computer tools like spreadsheets. Maybe you'll do some MATLAB or calculation software. Maybe you'll even run simulations. In step 4, you use some simplifying assumptions. Sometimes we have to make assumptions in order to simplify our problem. Here's some assumptions we could make when doing a solar panel cost estimate. For purposes of cost estimation, we could assume that electricity increases 2 to 3% per year to account for inflation. So we decide on some constant percentage to assume for inflation cost. We also assume a constant degradation rate as a solar cell's age. And notice that we also need to assume that the amount of sunny days per year remains constant. Because in order to make a cost estimate, we have to be able to make an educated guess about how much power each solar panel would generate. So next, in the last or second to last step, we solve the problem. In one of our lab activities, we may perform a calculation similar to this. Notice that you can actually perform the calculation and estimate how much cost will there be over 40 years for each solar panel option. And then based on this calculation, you could decide which option to choose. And here it appears that option 3 is the lowest cost over 40 years. So next, our final step is accuracy verification. This step is extremely important. You want to do the best you can to make sure that your calculations and solution are correct. Remember, in the real world, you're not necessarily going to be able to check your answer with your instructor or with your classmates. So you want to make sure that you take the time to double check your calculations. Let's go ahead and do one more review question here. This question's asking for the false statement about analytic problem solving. Take a moment and see if you can find that false statement. All right, well, let's take a look. What do you think about choice B? Is it optional to verify the accuracy of your solution? Yeah, not really. That's an important step, right? You need to do that. So choice B is the false statement. Okay, so let's move on to creative problem solving. Most engineering problems can often be open ended and complex. And so, if we're following the engineering design process, which is a creative problem solving process, we need to follow a nice approach. Our textbook recommends the following 6-step process. We ask ourselves first, what is wrong? Then, what do we know? Got to gather data. Number 3 is interesting. What is the real problem? This is key. As much as possible, you want to find the root cause of your problem. Because otherwise, if you don't solve the root cause, you might not be solving the actual problem, and you might be instead just putting a band aid on it. Next, you determine the best solution, figure out how to implement the solution, and then finally, we evaluate. We ask ourselves, did it work? Hopefully it did, but if not, we might need to go back and make adjustments. So let's go ahead and walk through this process with an example problem. Our first step is to ask us what's wrong. And pretty much this issue or problem, it could be any number of things. Maybe you need to optimize a process. Maybe you need to reduce cost, improve customer satisfaction, solve a reliability problem. Could be a lot of different things. And let's try a problem that's maybe a little bit easier to relate to. Suppose you are an engineering student trying to improve your grades. One possible problem statement could be, we want to find out why a student is getting low grades in their classes. So first, once we've defined our problem, we need to ask ourselves, what do we know? So we want to gather as much facts and data as we can. And notice, you don't try to evaluate the data yet. Right now, we're just trying to gather information. So for the student trying to improve their grades, we might gather their test scores, their quiz scores, maybe how much time they spent studying, their study habits, feedback from friends and instructors. You gather all this data. Then you move on to step 3. What is the real problem? This is a very important step. We want to find the root cause. So we want to look at our data and find out what the real problem is. There's two common methods that are actually used in engineering industry, which I would like to share. These are real methods used by engineers. So definitely give these a try. The first method I'd like to share is 5 whys. This is very common in manufacturing settings, and the idea is to keep asking why at least 5 times or until you find a solution, until you find that root cause. The second method is called root cause analysis, also known as structured problem solving. Or also known as model-based problem solving. And in this approach, you do almost a little bit of detective work. The idea is that you list all the possible root causes of the problem, anything you can think of. You list anything that could have possibly caused that problem, and then you use data and evidence to determine the actual root causes. So you try to use data to determine which of these are true root causes, which can I eliminate. These are excellent strategies to learn. Let's look at a couple examples. First, let's start with 5 whys. So the idea with 5 whys is you keep asking why until you arrive at the root cause. So we could ask ourselves, why were the students' test scores and homework grades low? Well, maybe the student didn't understand the material. That could explain it. Why didn't they understand? Well, the student didn't ask for help. Why didn't the student ask for help? Oh, well, they didn't come to class. That's tough. Why didn't they come to class? Oh, the student can't wake up that early. That's tough too. So why couldn't the student wake up that early? Well, they had to go to sleep late. Well, why did the student go to sleep late? Ah, the student had to work and then they had homework. Yeah, that's tough. But why did they have to work and finish lots of homework? Well, they're taking 24 units and they're working. That's an awful lot. Why is the choose? So notice now we're getting somewhere. Why is the student taking so many classes? Well, the student thought they could fit everything into their schedule. Why did they think they could fit all that into their schedule? This might be our root cause. Maybe the root cause of the problem has very little to do with the student's actual effort or ability as a student, but more due to the fact that their time management was maybe not as good as it could have been. Maybe the student needs to improve their time management and planning, and maybe be more mindful of how much they have on their plate. Let's look at another example. This is a really powerful technique. I personally have used this many times in industry to solve problems, and I highly recommend it. The other advantage of this strategy is if you are working on solving a problem and it's taking you time, you can actually show your data table with all of your progress to your boss and to your team. And that way, everybody can see what progress you're making as you're working on the problem. In fact, when I was in manufacturing, there were a few meetings where we were not allowed to come to the meeting without one of these tables made, because the expectation was that you were going to go through and identify that root cause. So Let's see how this structured problem solving process works. So, the idea here is you list all the possible root causes as rows in a table. So, normally I probably would have done this table in a spreadsheet or document so I had a little more room, but this is just a quick sample. So here we have the root cause, and we've listed some of the root causes. And look what we do next. We look at our data and we determine what evidence supports that root cause, what evidence does not support that root cause. And so notice you can go through and you can figure out, well, maybe this one's not likely to be the root cause because there's a lot of evidence against it. Maybe there's a lot of evidence against this other one. And once you've identified some possible root causes, you can collect more data until you are able to confirm the root cause. The other advantage of a table like this is if you ever need to convince your team or your coworkers about what the root cause is, these tables help you show all the data you've looked at and summarize why what you have identified is indeed the root cause. So this is an excellent tool. I highly recommend it. Once you've found that root cause, it's time to move on to deciding a solution. So here we typically brainstorm and we generate a list of possible solutions. If needed, you might also confer with other coworkers or experts as needed. So the idea is you go through, and for this student, maybe they needed to change their time management. Maybe they needed to drop a few of the classes that they could take in a future semester. You figure out a plan and figure out a solution for that problem. And then finally, once we have decided on what solution we'll take, we implement the solution. Implementation is sometimes easier said than done. It can be very time consuming. You can imagine if a company is launching a product or launching a software update, implementation can be a significant effort. So it can require a lot of time and money, communication with customers, approval processes, all sorts of things. So implementation is a very important step. For example, in manufacturing, there's often very formal review process that needs to be followed for any changes or updates made to products. For the student's case, the best approach would probably be to try a proposed solution and then monitor for improvement. Depending on whether or not there's improvement, adjustments could be made to the solution. Finally, our very last step is to evaluate the solution. This is important. You want to make sure that you actually solved your problem. So you need to evaluate to make sure that you met the objectives. And depending on the results, you might be finished. Maybe you need to go back and make changes. So maybe you meet with that student again after a set period and determine whether their problem has been solved. So lastly, we'll finish up with a few more ideas to keep in mind while solving problems. First is this idea about personal problem solving styles. So a lot of research has been done about how to make people solve problems better. And one idea proposed here is that people generally prefer operating in one or more of these four areas. So some people like to generate, where they're gathering information, imagining ideas. So these people love thinking of ideas, but they don't really care too much about actually implementing the ideas. There's also people who conceptualize. These are people who make sense of information and put ideas together. Then there's people who optimize. So these people, they're impatient, they don't like ambiguity, they're good at action planning, they want to find the best option possible. And finally, we have implementing. These people like to learn by direct experience. They prefer to get their hands dirty and try things rather than sitting around and running tests and simulations. So the idea is that you may tend to prefer one or more of these styles, but teams generally need all four of these styles to be successful. So if you try to recognize your own preferred style and find others to work with who have different styles, you may be more successful. So, a couple other things to point out about this. Once again, I don't expect you to memorize all the details of problem solving research. The important thing to know here is that everyone solves problems differently, and in many ways, that's a huge benefit to get everybody else's perspectives on a problem. So, again, the idea here is that if you know what type of problem solver you are, try to, try to surround yourself with people and opportunities which support your problem solving style. All right, we have just a couple more points to share. We mentioned brainstorming, and brainstorming is an important part of creative problem solving. In brainstorming, we try to think about as many innovative ideas as we can. And generally, this is used for creative problem solving, but also sometimes analytic. And there's a lot of strategies to help your brain think outside the box. Here's one of them. You can use this acronym called SCAMPER. SCAMPER. These are questions you can ask yourself in order to think of new ideas. For example, can you substitute, combine, adapt, modify, put to other use, eliminate, reverse, or rearrange? Basically, questions to ask yourself about your problem or solution to generate new ideas. One more important thing to know about brainstorming is there are ways to make brainstorming more effective. If you're brainstorming on your own, you want to find a place free from distractions, write ideas down without criticizing them, and if possible, do individual brainstorming followed by a group session. Group brainstorming can also be really powerful. More people means more ideas. Group brainstorming gets others involved, but notice this. There are some recommended guidelines on how to facilitate these sessions. Please make sure you remember these guidelines. I'd especially like to draw you to this guideline number 3. You want to make sure you keep the group between 6 to 12 people. You don't want to have so many people in your brainstorming group that you get distracted or that you can't listen to everyone. So make sure you remember, try to keep the group fairly small. Great to have a facilitator to take notes, keep everyone focused. Define the problem so everyone's on the same page. Keep the group small. Let everyone know if you're following a set process to generate ideas. Write ideas down so that everyone can see them. Involve everyone. Make sure everyone gets a chance to speak and share. Very important, don't evaluate. You don't want to dismiss the crazy or dumb ideas. They might actually be pretty good. Eliminate duplicates. So if you have repeated ideas, make sure they're truly duplicates, but then delete them. And also, you can even have everybody pick their top 3 favorite ideas that they like the best during the session. So finally, we'll end with the last point to think about. We'll talk more about critical thinking later, but one thing to keep in mind with critical thinking is that many issues and problems are not going to be solved quickly and easily. And sometimes our own background and experiences can limit our thinking or give us biases. So it's important to try to think critically as much as possible. Critical thinkers will continually ask why throughout the problem solving process. They'll question why they think a certain way and do their best to solve problems objectively and effectively. All right, so that's it for today's class. Hopefully now you are more comfortable with dimensional analysis and estimation. We've also previewed analytic and creative problem-solving strategies. I highly recommend that you think about what strategies work best for you. And if you can, try out the 5 whys or structured problem solving. Also, take note of those strategies for brainstorming and keep the group small if you do a group session. Finally, if you get the opportunity, try using those real techniques, like structured problem solving and 5 whys. Even for problems unrelated to engineering, those techniques can be really powerful. All right, well, thanks everyone for joining the video today. Feel free to reach out if you have any questions, and we'll see you in the next video.